Thanks for the introduction and for correctly pronouncing my name. And thank you also for all the work, for organizing that workshop, to the organizers, and for inviting me. It's a great pleasure and honor to be here. I had a lot of intense and exciting discussions. I'm happy to have more of them today. And as Anna just said, there's a lot of superradiance in our life nowadays. So after the talk by Markus Greiner, I will continue with some work on the observation and characterization of superradiant bursts, which in our case take place in a cascaded quantum system. And I will tell you what I mean by that. So still, let me start by recalling that when you have one or many independent atoms, you usually expect an exponential decay of the excited state population and thus also of the fluorescence that you may detect on a detector. But if the atoms emit collectively, then you have both a possible speed up of the decay, but you can also have qualitatively different effects, in particular a non-exponential decay, a so-called superradiant burst, where the intensity of the emitted light first increases, reaches a maximum, and then quickly decays. And such collective radiative effects have both like interest for new technologies. For example, James Thomson was here. Is he still here? No. He works on superradiant lasers, which may have very narrow line widths, and you may also try to use such collective radiative effects to generate photonic quantum states of many photons, multi-photon states. And it's also, and I guess this is why I'm talking about it here, it's actually interesting because it's a challenging many-body quantum optics problem. So where the geometry plays a role and also the symmetry of the coupling between the emitters plays a role, and you may observe complex phenomena like superradiant phase transitions, for example. And for such collective emission to take place, we need to fulfill some, say, requirements. Particularly, the atoms have to, or the emitters have to see each other or emit into one and the same mode. And that can be realized by having all atoms nearby, so very closely spaced, but you can also put them into a cavity where they collectively couple to the cavity mode, or if you have some, say, ordered array with small spacing, then you also have a mode which is singled out into which this ensemble may strongly couple. And so there's, as I said, many systems, more than those. And the one we work with is actually laser-cooled cesium atoms, which are coupled to the mode of a so-called optical nanofiber. So an optical nanofiber is a cylindrical dielectric waveguide with a diameter smaller than the wavelength of the guided light. Typically, it's half of the wavelength, and in that case, for silica and the refractive index of silica, about 50% of the optical power propagates outside of the waveguide in the form of an evanescent wave. So you can imagine the intensity profile to look like such a Mexican hat, right, where a lot of light is outside. And if you now couple an atom to this evanescent wave by putting it sufficiently close to the nanofiber, say 200 nanometers away from the fiber, then it will absorb a few percent of the guided light, say 3% in our case. And if an atom is excited at that distance and decays, then about, say, a bit less than 1% of the emission will go into the nanofiber guided mode. But for that to happen, you have to actually have the atom feel as if it was in free space, happily emitting, and just like coupling to the guided mode without being perturbed by the nearby hot nanofiber surface. And the way we achieve this is that we trap the atom using detuned fiber-guided light fields. So more in detail, the nanofiber is realized as the waste of a tapered optical fiber. So this is a step index fiber which you heat and pull, and it gets narrower and narrower like a chewing gum. And we do this in a very controlled way until we have a diameter of, in this case, 500 nanometers. And the guided light is coupled adiabatically from the step index fiber, from the single mode step index fiber, into this nanofiber guided mode and out again. And then we launch a red detuned light field with respect to the atomic transition from both sides, creating a red detuned standing wave and a blue detuned running field, which creates then like just cylindrically symmetric intensity profile. And the joint action of these two light fields, so red detuned light fields tend to attract polarizable particles into the intensity maxima. So this red detuned light field will attract the atoms towards the fiber. The blue light field will repel the atoms from the fiber. But the magic is that the red light field has a longer decay length than the blue because it has a longer wavelength. And so when the atom approaches the fiber from a distance, it will first see the attractive red potential, and then nearby it starts to feel the repulsion. So if you choose the intensities and detunings right, you can have a stable minimum of potential energy at a distance of 200 nanometers from the fiber. Then using the interference of the counterpropagating red, you have a standing wave so that you can actually have a spatially periodic arrangement along the fiber, and we can also confine in the azimuthal direction playing with the polarizations of the light fields. So in total, the trapping potential looks as shown here. We have two diametral periodic arrays of trapping minima along the fiber, and we can load atoms into this trapping potential from a magneto-optical trap. The loading is such that we never have more than one atom, but whether there's 0 or 1 is random, okay? And now we work with these atoms, and there's a interesting feature which comes from the modes of these nanofibers, which have special polarization properties. Actually, their polarization depends on the direction of propagation, and this so-called spin momentum locking of light, don't let me go into the details, just take my word for it, allows us to have a so-called directional, or also termed chiral coupling, where the atom does not emit symmetrically into the waveguide as shown here, but we can actually reach a situation where experimentally more than 10 times more light goes, say, to the right than to the left, okay? And this means that if we now have an ensemble of atoms coupled to the fiber, and all of them are chirally coupled, so emit only to the right, then any given atom will only interact with downstream atoms, right? So there's a unidirectional flow of information. So say this atom does not know anything about the fact that there are other atoms, and this one doesn't know about any of the downstream atoms. And one can ask whether there are actually collective effects of the type that I was explaining in the beginning, because the superradiant burst that I was showing was predicted in the case of the so-called Dicke model, where you assume that the coupling between the emitters is symmetric, right? That both emitters act equally onto each other. But here we just have this cascaded quantum system. Is there like a superradiant burst in this case? And actually, to study this, we started by probing our system by launching very short excitation pulses through the fiber, and then looking at the transmitted light as a function of time, okay? And we can do this with a pulse which is much shorter than the lifetime of the excited state of the cesium atom. So the lifetime is 30 nanoseconds. We launch a 5 nanosecond pulse through the fiber. This pulse will excite the atoms, then it's off, and we look at the decay emitted into the fiber. So here I separate the time into the time of this excitation pulse from -5 to 0 nanoseconds, and then comes the time afterwards where there's the fluorescence of this, or collective fluorescence of the atoms, which goes into the fiber and is recorded. Maybe we start first here with this side. Actually, the nice feature, because all the atoms are very efficiently coupled to this well-defined mode, is that we can actually compare the pulse without atoms. It's this blue shaded area. And then we can measure what comes out with atoms. And then simply integrating this blue shaded area here, we can actually count the photons that were absorbed by the atoms. So we have a direct measure of the photons absorbed by the atoms. And then looking after the switch off of the pulse at the fluorescence, you see that when there's no atoms, then there's no light. That's this blue line. But when there are atoms, we have fluorescence. So also here, this red shaded area is a direct measure of the integrated power over time of the light emitted by the atoms into the waveguide. Okay, and now what we see here in the absorption is that for the very weak excitation, so this here is actually you measure this excitation in terms of the so-called pulse area. So it's the integral of our Rabi frequency over the pulse duration. In this case here, it was much smaller than pi, so about 0.02 pi. And in this case, what you see is that there's a polarization of the atom that builds up and that starts to absorb more and more the light that goes through the fiber, but it's essentially here an exponential behavior. But if you crank up the pulse area, then you start to see that the atoms do a Rabi oscillation. They start to saturate. So you turn the Bloch vector while the pulse is absorbed more and more. There's less absorption per unit of time here, and so this thing starts to bend over. And here, for a pi pulse, you see that it really goes up, and the atoms are, to a large extent, all excited along the waveguide. Okay, and then mind that there's a different like power scale here. So because we change this pulse area by changing the Rabi frequency, so we increase the power. And what you see is that the fluorescence compared to the excitation pulse, of course, gets less and less. But I think in order to analyze that more quantitatively, it's good now to extract these quantities, like how many photons are absorbed per atom as a function of the pulse area. This is the first thing I plot here. Then you see, they do some damped Rabi oscillations. But if we stop at this excitation of pi here, a pi pulse, then we have about 80% excitation probability. So it's a highly excited ensemble of atoms coupled to the waveguide. And if we then look at the number of photons emitted into the waveguide after the excitation per atom, then there's some, I mean, if you look at it for the first time, it may be surprising that what you see is that the number of emitted photons per atom is not maximum when the excitation is maximum, right? But it actually has a maximum which is clearly off the point of maximum excitation. And so what you can now do is divide the two and find out, so how many emitted photons do I have per absorbed photon? And then you see that the emission efficiency, also the coupling efficiency of this ensemble into the waveguide is actually varying. If I have a weak excitation, I prepare a time decay state in the single excitation regime. So this is like a spin wave, which exactly matches the propagating mode of the fiber. If that decays, it goes into the fiber, and we have some 60% probability of recovering that excitation. But, and remarkably, if you go to a pi half pulse here, right, you still have 50% emission probability. And this is about where the total number of photons per atom emitted into the waveguide peaks. But if you then go to a pi pulse, then the atoms are actually all excited, they start to emit independently. And so you go down to the single atom emission efficiency. Okay, so for the fully inverted ensemble, we find here in these experiments that the single atom value is again recovered. But we have a large collision efficiency, not only for weak, but also for moderate excitation. Okay? So now how do we you see here some models. Also in the previous slide, you had some theory curves, and since we have also some interest in theory in this workshop, let me tell you how we describe theoretically the results. So for the weak excitation, it's simply only linear response theory. So what we do is we take the amplitude transmission coefficient, which is depending on the detuning for each atom. It's a Lorentzian, right? Or it's a Lorentzian dip, where the coupling efficiency goes in and the line width of the atoms and the detuning. And if I have n atoms, then this is just the single atom transmission to the power of n. And what I now do is I take my input light pulse, I Fourier transform it, I filter it with the transmission function, I do the inverse Fourier transform, and I have the output electric field. And this describes perfectly what comes out in this weak excitation regime. If you go beyond weak excitation, then there are different levels of theoretical complexity in the description, but what works remarkably well for our results, also for very high excitation, is that we take what we call the coherent state model. So we take a cascaded quantum system, so that makes our life easy. We can easily compute it because we now consider that the first atom is driven by our incoming laser pulse, okay? And then we compute what this atom does by solving the master equation for this atom, and then take an input-output formalism where we, however, consider that the next atom downstream is only driven by the coherent component of the resulting light field here, right? So we take here the input light field, it interferes with the coherent component radiated by this first atom and gives rise to the next coherent field. And we, the approximation is that we consider that the dynamics of this next atom is only due to the coupling to this coherent component, okay? But of course, if you look at the power, then there is also just incoherent spontaneous emission of this atom, which is not included in this coherent approximation. And that means that the power that comes out of my waveguide is not equal to just the modulus squared of my coherent amplitude, but I have to add this incoherent part here, okay? And this works remarkably well for pulse areas going from 0 to almost pi. And the nice thing is it can be easily solved for 1,000 atoms because of this cascaded character where you just do one after, do this consecutively, one after the other, okay? Now, let us look at what happens if we increase the atom number. So we now go to this pi pulse condition where we invert our ensemble and we look at the decay of this ensemble as a function of the atom number. So for 130 atoms, we do see something that can, within the noise, still be described well by some just exponential decay. But at a value of about 200 atoms, we start to see that here in the beginning, the fluorescence decays almost not, so there's the derivative is flat. And if we go even higher, then you see that the intensity increases, and we clearly have a signature here for 1,000 atoms of a burst that is emitted by the atoms. So the first statement is the burst also occurs for cascaded quantum systems, and I should stress that this is in agreement with recent theoretical predictions about such cascaded coupling of atoms to the waveguide. Now, in the Dickel superradiance that I was describing in my introduction, I said that this peak intensity here grows with the number of atoms, right? So the more atoms I have, the higher the peak intensity and the shorter the pulse. And it turns out that in the Dicke model, this peak intensity here should scale like the square of the number of atoms, because if the atoms emit collectively, their dipoles add up, and then I like take the square of these n dipoles, I get n squared. So we measured this peak power here as a function of atom number, and there's an interesting scaling here of this peak power. So below this threshold of the burst, sorry, here is 100 and here is 1,000. Okay, sorry, I cut this off. So below this burst threshold, the scaling is just linear with n. So you put twice as many atoms, you have twice as much power because the atoms emit independently. But then when the burst starts to appear, we have a scaling that is faster than for the Dicke case. And this is actually surprising, right? So we have a power of 2.6 here, but it turns out that this is because of the geometry here of our setup. We have a mode which is defined by the fiber. The dipoles of the atoms start to synchronize, and you can imagine that like a phased array. If you add more and more atoms, then there's an emission characteristic which closes down the NA, and more of the emitted light goes into the numerical aperture of our waveguide. Yes?
So this crossover, the critical atom number, does that depend on the light-matter interactions?
Yes, thank you for the question. So the question is, does this crossover here depend on the beta factor? And absolutely. So I mean, in essence, you want a high OD ensemble, and you can replace atom number by beta in order to get the same threshold. Exactly, thank you. Now, again, let us now go compare these theoretical descriptions, because it turns out that we have an issue of describing the burst with this coherent state model if we go to the to a fully excited system. So I compare here, so in order to be able to compare it to the truth, so to speak, what we have to do is now to assume a larger beta factor, and this is exactly your question. So here we assume now a beta factor of 0.4 and only 10 atoms, because then you can solve the master equation simply, and you know what a system with these parameters will really do. And then we compare this master, so the truth is red in all these curves, and I go from 10% of a pi pulse to a pi pulse here, right? A, B, C, D. And I compare the master equation with our coherent state approximation. And you see that for 10% and 50% and even 80% of pi pulse, our coherent state approximation still does a reasonably good job and matches the master equation result. But when you go to a fully inverted ensemble, then the orange and the red line are completely off, because so there is no coherent component in the decay of the atoms anymore if the atoms are fully inverted. There is no coherence, they decay spontaneously, and so in our coherent state approximation, this alpha that I was writing down between the atoms is 0 everywhere, okay, because we only have incoherent emission. So in order to solve that and still have a reasonably simple model, we established the mixed coherent state approximation. So the mixed coherent state model, I just give you the idea, is that we consider that the atoms are driven both by the coherent component, but to this coherent component that we had before, we add a small coherent field with arbitrary phase. Okay, so you can picture this in the complex plane like if this is my coherent state, then I add another coherent state to it and I average over it, and the power contained in this incoherent, what we call incoherent state, here it's a coherent state with arbitrary amplitude, matches the incoherently emitted power. Okay, so this is a simple model where all we have to do is to average over this phase here, and it turns out that only taking 10 values for this phase already gives you a very good description, so it's still computationally very simple to do the modeling. And then this gives perfect description of what we see. Now you can ask, what are the coherence properties of this burst light? So let us first turn to first order coherence, so field-field correlations, right? And we can measure that just via a heterodyne scheme where we interfere the burst with the laser light that was like exciting the atoms. And if we do that as a function of pulse area, so look at the first here, then we see interference fringes in the heterodyne signal between the burst and our laser for pulse areas smaller than pi and for pulse areas larger than pi. But if the pulse area is more or less pi, you can ask me why it's not exactly pi here, but let's say it's pi here, then you see that the interference disappears. So the burst, if the ensemble is fully inverted and decays, is incoherent with anything in the universe, right? So there is no phase relation, it's spontaneous emission. But what we then did, so this is measuring the coherence of the burst with respect to the laser. What we then did was to measure the coherence of the burst with respect to itself. So we took the field emitted at the beginning of the burst with and like correlated it to the field at a later time, okay? And what you then see is that as for the coherence with the laser, it is coherent with itself before, I mean, if I have less or more than a pi pulse, but it's also fully coherent with itself if it is a full pi pulse. So the burst is coherent with itself. And so when we saw that, then in the beginning we said, or I said, that means this is a collective phenomenon, like the dipoles synchronize, and in the beginning there's a coherence with respect to the end. But it turns out that no, this is not a sign of collective emission, because what I had to learn, and we had a lot of arm wrestling about that, is that you would find exactly the same thing as we see here for the emission of a single atom. Okay, so even the spontaneous emission of a single atom will give you a G2 of 1. I didn't know that. I don't know if you knew it. You can scratch your head about it, but that's true. So an atom which decays, thank you, actually will have a coherence between its emission in 1 year and right after the pi pulse. Okay. So, however, the observed large first order coherence indicates that the emission goes predominantly into one mode, and that I learned by talking to Klaus Möllmer. If you don't understand something, or if we don't understand something, we talk to Klaus, and then he said, yeah, we have a paper about it. So actually you can show that the fact that the burst is coherent with itself means that the emission of the burst goes into a single spatio-temporal mode. Okay, and actually in these experiments we were now able to measure this contrast of our heterodyne signal. Let's just look at this purple line here. And you see that it's only in a very narrow range of pulse areas that the coherence get lost. And actually the width here is depends on the number of atoms. So if you have less atoms, that's wider. If it's more atoms, then it's narrower. We can also discuss if there's an intuitive picture for the width of this loss of coherence. Now for the last 4 minutes, I would like to turn to second order coherence, so the latest results. So now we don't interfere the light with a laser here, but we actually have a hand-buried Brown twist setup where we take the fluorescence light and look at the second order coherence of the burst. If we just look at the bare coincidences here, then so of course now we have to consider G2 function, which depends on 2 times. So usually one is used to the G2 of tau, where tau is the waiting time between the 2 photons. But this is only a good measure if you have a like steady state signal. We have a burst, so we have to ask what is the probability for having a second photon provided at time t2, provided that I have a photon at time t1, right? And that depends on t2 and t1. So what you will see now is g2 of t1, t2. But here I just have the bare coincidences as a function of t1 and t2, and then if I have such a burst, then this will peak at the peak position of the burst, of course. But if I can now normalize this to the count rates at time t1 and t2, and this then gives me the g2, so the second order quantum correlation function. And if we plot this quantity here as a function of time during the burst emission for excitation pulses below pi, at pi, and above pi, then what you get, or what we see, is these black dots here. So here, again, we have a pulse area smaller than pi, and the second order coherence, or the G2 of T1, T2 is 1, which means that the light emitted by the atoms is second order coherent from the beginning, right? The same is true for a pulse area larger than pi. And the reason is that the coherence of the excitation laser, if you have more than a pi pulse or less than a pi pulse, is still in the ensemble. I mean, there is a projection of my Bloch vector onto the equatorial plane. There is some kind of coherence in the ensemble, and that coherence is then amplified in the emission, but it's there from the beginning. But now let's turn to the situation where I have the superradiant burst in the condition of full inversion. And then you see that in the beginning, I have a G2 of T1, T1 here, so the same times, of 2. And this means that the atoms are emitting independently. Thank you. So you have an independent emission of atoms in the beginning, but as the burst emission goes on, second order coherence builds up and it goes to 1. So we have an emergence of second order coherence in the emission. And we will have more of that in the next talk. But let me just say that the theory curves that you see here took a long time to produce. We had to work together with Michael Fleischhauer and Christopher Mink, and it's a very gifted postdoc, Felix Stemmen-Johanns, who established the truncated Wigner approximation model that quantitatively describes the second order coherence. So maybe this should be the last thing that I then show, which is now let us look at the initial value of G2 of T as a function of pulse area. So we saw that for below and above pi, I have a G2 of 1 because the coherence of the laser is still in the ensemble. But if we get close to 1, then, so a pulse area pi, sorry, then it peaks and has a maximum value of 2. But if we now just assume naively that we have like the same Rabi angle for all atoms and assume that the atoms at the start are in a product state of all atoms pointing to the north pole of your Bloch sphere, then you would indeed expect that this curve here peaks where the dashed line is, so we can take this and compute using like theoretical prediction here, the value of G2, and it predicts that the atoms emit independently, or that we have when we have full inversion here. The fact that we go a bit to higher values of pulse areas in the experiment is because the excitation pulse, when it propagates along the atomic ensemble, will be gradually absorbed. And so we have a bit more than pi in the beginning and a bit less than pi. And there are such effects which have to be actually fully modeled if you really want to get a prediction. And so this truncated Wigner approximation calculation here takes really also the excitation process into account. And then you find that you have this maximum value of G2 for about 1.06 pi. Okay, I think that I will just skip this and talk about one thing that we observe, but that we don't yet fully understand as an intuitive understanding, which is if we now look at the second order coherence function for unequal times, so this then has to be plotted in a 2D plot where I put T1 and T2 on the two axes, then we see that while we have for the burst emission in the beginning this high value of 2 which goes down to 1 over time, so for equal times, if we now correlate photon-photon correlations for different times, we see that for a long time difference between T1 and T2 we get anti-correlations. So if we plot this line here, so Tg of T1 equals 4 nanoseconds fixed and T2 larger than 4 nanoseconds, we see that we start with a G2 of 2, so uncorrelated atoms, but interestingly it goes below 1, so we have anticorrelations after a while. And this is probably due to the fact, or it hints on the fact that in the single realization, the burst is much shorter than the average burst that we observe, because we observe bursts over many, many realizations. But if you now consider that the individual burst is short, then it makes sense that if you see a photon in the beginning, there won't be photons at the end because the burst is already over. And if there is a variable waiting time for the burst to occur, and this is something that you expect also in the Dicke model, then you would expect that if there's no photon at the beginning, then it's more likely to have photons in the end because the burst comes late. And indeed, if you do again a full quantum calculation of the Dicke model in the case of 10 atoms, you see that you expect such a behavior. So there is actually a qualitative agreement between our data and theory for a Dicke model, but for our cascaded quantum system, we don't have a theoretical description of this effect as of now. So this is really something that goes beyond what standard theory at the moment is capable of giving you, this G2 of T1, T2 with unequal T1, T2. So let me summarize. We observed a superradiant burst in a cascaded quantum system. We measured the first and second order coherence. We could confirm that the burst is emitted into almost a single spatiotemporal mode, and we saw that during the emission of the burst, the second order coherence builds up, which really indicates now collective decay dynamics. And we observed anticorrelations in unequal time correlators, which still look for theory description here. So where can all this lead us? So actually this truncated Wigner approximation is only valid for short times, but we can also wait for a long time and study the in subradiant states. And we actually already observed for high excitation that there's a kind of superradiant ringing, so that the emission switches off, switches on, switches off, switches on for a long time. So this is an interesting dynamics. We are thinking about continuously driving incoherently this ensemble, and you can then ask, is there something like superradiant lasing without mirrors in such a cascaded quantum systems? Will you see a line narrowing of the atoms emitting collectively when they are driven? What I find interesting as a question is, if we now have such a burst which tells us about all atoms, but in principle there are many photons, couldn't I do a measurement on the burst and measure the phase of this light field and put the collective Bloch vector back? So can I stabilize this collectively decaying ensemble by making a feedback of my measurement? And I think that what we see is that these experiments can be used as a benchmark of state-of-the-art simulation methods for many-body quantum systems. And with this, I would like to thank Philipp Schneeweiss, who is supervising this project, Felix Tebben-Johanns, the postdoc, Constanze Bach, the PhD student, and former PhD student Chris Liedl and Sebastian Pucher, and I thank the Alexander von Humboldt Foundation and you for your attention. Take questions.
Hi, cool result, of course. Sorry. I mean, in the early days of superradiance, like the theoretical days in the beginning, there was always a big emphasis on the delay of the pulse. So there is no light coming out for a while, And then this pulse, and there's a lot of statistics because the delay can be even bigger than the size of the pulse. In your case, it always seems to start at the beginning with a linear increase, never this quadratic enhancement of the intensity. Is this the remaining phase, or?
Okay. Yeah. So first of all, I mean, I think that as I said, I think these anticorrelations in G2 show that indeed we do have a variable delay and a shorter pulse. And what I'm showing when I show I mean, here I have one. If I show this result here, then I show an averaged intensity profile, averaged over many, many, many pulses, right? And now you're asking, why don't I see something which probably
be not zero?
Yeah, why is it not zero? I mean, the theory says so. So do I have an intuitive explanation? Maybe it's just because for the moment the ratio between the length of the pulse and the delays is not yet there where you would see it. I agree that in principle. I agree that in principle, even when averaging, if the delay was much larger than the pulse, then you should see something.
Could this be a consequence of your sort of chiral coupling, or is this?
Good. I mean, yeah, good question. So, I mean, we do see a burst, and in the paper we say it's remarkable the similarities, given the fact that the Hamiltonian is completely different. I mean, the symmetry goes into the predictions for the Dicker model, right? And so it could be. It's a good question. I haven't thought about it. Maybe it's a chiral case which leads to this behavior.
So thank you, Arno. That's very interesting. I have some questions I ask you. The first one regards the superradiant burst you showed there. There seems to be, maybe I'm dreaming, like a small knick after the decay. Do you understand where it comes from?
You mean it goes down and up again, right?
Yes.
Yeah. So it turns, we have observed that in the low excitation limit experimentally, and it's also a known effect. What happens is that in this geometry where you emit along an ensemble, you actually cycle through subradiant states because the downstream atoms are driven by the upstream atoms and get a phase shift between the driving atoms and the downstream atoms. So let's say, maybe I shouldn't stress it too much because that's in the low excitation regime. And interestingly, we do see similar behavior also in the high excitation regime, where you see that the emission actually stalls and goes up again and stalls and goes up again. And you can understand it if you think about the fact that, let's say you drive, in the low excitation regime, you understand it by saying the atoms are in the beginning all in phase, but then you start to actually they Rabi oscillate and start to radiate a field which is in phase opposition to the driving field. And if this field drives the downstream atoms, you start to have actually phase sign changes of the phase between the atoms along the ensemble, which can fully cancel the emission into the waveguide. So there's a continuous cycling in the lower excitation regime from the superradiant through all n-1 subradiant states. But this is something that is known and easy to predict. Here, if you want to predict this for the fully inverted ensemble, where it also seems to happen, you would need a theoretical model which is capable of predicting the long time dynamics, and the truncated Wigner approximation is known for not doing that. So currently we can't.
And do you see the features of this in the correlation functions that you measured?
So we have not looked at that. So if you look at our data for the correlation function, then you see, given the fact that the intensity, look here, given the fact that the intensity is very low, the uncertainty on these measurement points here. So the blue is the burst, okay, the blue shaded area. So here you see that the burst goes off, and I get large error bars because there's not enough intensity for our signal to noise and averaging times to make reliable predictions about G2 for long times. So then the answer is we can't, in the current state of the experiment, see what happens to G2 when there's this switching on and off.
Okay. No. So I guess then this next question is...
I think in the interest of time, let's actually stop there. Thank Arno
okay, I
again.
see it and it doesn't answer. How does it scale with n?
Okay. Let's stop. Okay, thank you.